Good morning, one and all. My name is Ram Babu, lecturer in chemistry, Government Degree College, Perumalpuram. In this video, we will discuss about the metal carbonyls. So, this is a third semester topic. So, the components of this video are the definition of metal carbonyls and classification, preparation of metal carbonyls, and structures of some metal carbonyls. So, all these topics can be discussed in this particular video. So, what are the metal carbonyls? So, that is the compounds which are formed by the carbon monoxide with most of the transition elements like the iron, cobalt, nickel, and etc. So, those particular compounds are called metal carbonyls. So, here the basic example is the NiCO4, nickel transition elements forms these particular metal carbonyls. And then classification. So based on the number of metal atoms per a molecule, the metal carbonyls can be classified into two types. Those are the mononuclear metal carbonyls, and second one is the polynuclear metal carbonyls. So first we are going to discuss about the mononuclear metal carbonyls. What are that mononuclear metal carbonyls means? The metal carbonyl that is having one metal atom per a molecule. So such type of metal carbonyls are called mononuclear metal carbonyls. For example, NiCO4, FeCO5, all these are all the mononuclear metal carbonyls because these are having the only one metals. That is, Ni having one nickel and FeCO5 having the one iron. And then the polynuclear metal carbonyls. Poly means many. Here the here the metal carbonyl which contains two or more. So at least the metal carbonyl having two metal atoms per a molecule. So such type of metal carbonyls are called polynuclear metal carbonyls. For example, Mn2CO 10 times and Fe2CO9, that is manganese decacarbonyl and iron nonacarbonyl, or these two having the two manganese atoms and two iron atoms. So that's why these two are comes under the polynuclear metal carbonyl. And then in this next slide, we are going to discuss about the basic differences between the MNMCs and PNMCs. That means the mononuclear metal carbonyls and polynuclear. Here, MNMC is having the formula MCOX times. That means only one metal here in this molecule. While the PNMC is having the general formula MXCOY times. Here, where X means the number of metals that should be greater than 2. There is that formula difference. And the next difference is so the mononuclear metal carbonyls are soluble in organic solvents. Mononuclear metal carbonyls organic solvents lo dissolve అవుతాయి. And then the polynuclear metal carbonyls means these are insoluble in organic solvents. So ఇవి ఆర్గానిక్ సాల్వెంట్స్లో కరగవు and they cannot be decomposed. So mononuclear metal carbonyls are cannot be decomposed at ordinary temperatures, while the polynuclear metal carbonyls are decomposed below its melting point. And then the next difference is the mononuclear metal carbonyls are more volatile, and then while the polynuclear metal carbonyls are less volatile. And another difference is that does not contains metal-metal bond because the mononuclear metal carbonyl have only one metal. That's why there is no existence of the metal-metal bond, while the polynuclear metal carbonyls have two or more metals. That's why they may contain metal-metal bond. These are the basic differences between the mononuclear metal carbonyls and the polynuclear metal carbonyls. And then next we are going to discuss about the synthesis. That is the preparations. First synthesis is direct synthesis. This method is limited to the carbonyls of the metals which can be obtained in the active form by low temperature active form. So those particular metal carbonyls can be prepared by using this particular synthesis. So first example is the preparation of nickel tetracarbonyl. So nickel is very reacts with carbon monoxide at room temperature and a normal pressure. So there is nickel can be reacted with 4 carbon monoxide molecules at 40 degrees centigrade temperature. It will give the nickel tetracarbonyl. And then another example is the preparation of iron pentacarbonyl. So here the carbon monoxide is passed over the reduced iron at 110 degrees to 220 degrees centigrade and 50 to 20 to 100 atmospheres pressure. So that is that high pressure and high temperature reduction process here. So iron reacts with 5 carbon monoxide molecules and gives iron pentacarbonyl. And that is that the the one method of preparations we can discussing in this particular sample video. And then the next one, and effective atomic number rule, EAN rule. For the metal carbonyls, EAN rule is very important rule. So why some of the metals can be combined with 4 carbon monoxide molecules, and some of the metals reacted with combines with 5 carbon monoxide molecules? That particular question can give the can be achieved, answered by using this particular the EAN rule. What is the EAN rule means? So while a particular a metal can forms the metal carbonyl, it can acquire the number of electrons present on a metal its own, and can be those gained during the bond formation. That means, so during the formation of a metal carbonyl, so the metal can gain some of the electrons from the carbon monoxide molecule. So that particular number can be that can be number that electronic atomic number can be equal to the next noble gas. That is, the metal can continues to accept the lone pair of electrons from the carbon monoxide ligands till their atomic number becomes equal to the atomic number of the next inert gas next to that element. For example, the EAN is equal to atomic number of the metal plus the number of electrons gained from the ligands. Or simply, the EAN is equal to atomic number of the metal plus 2 into number of carbon monoxide molecule. So various examples can be discussed. So for this particular EAN rule means, here in this particular table that gives the idea. For example, CrCO6 times, that is chromium hexacarbonyl. So here the atomic number of the chromium is 24. The number of electrons donated by the carbon monoxide molecules means, here the 6 carbon monoxide molecules are there. So that way, so 6 into 2, that means 12 electrons can be gained from the carbon monoxide molecules. So that the chromium acquires so 24 plus 12, that is 36 krypton atomic number. So it is an inert gas. That's why this chromium has the chromium hexacarbonyl having the stability. So while the nickel tetracarbonyl, so another example, so that is nickel have the atomic number 28. So it is having the 8 electrons deficiency from the krypton. So that's why it can gained the 8 electrons from the carbon monoxide. So 8 electrons can be gained, means that is 4 it can combine with the 4 carbon monoxide molecules. That is, it can form nickel tetracarbonyl. So as a result, it can acquire so 28 plus 8, 36 electrons. In this way, so all some of the metal carbonyls having the fixed number of ligands during the formation of the compounds. That means FeCO5, another example. So in this particular FeCO5, iron is having the atomic number 26. It can gain electrons from the ligands. How many electrons it can gain? That means 26. It can 10 less to the krypton atomic number. So that way it can gain 10 electrons from the carbon monoxide. So 10 electrons means 5 molecules, 5 carbon monoxide molecules, 5 into 2, that is 10. So as a result it can acquire so krypton atomic number. While the molybdenum hexacarbonyl MoCO 6 times. What is the atomic number here? The 42. So next another gas is xenon, that is having the 54. It can less 12 6 6 into 2, 12 electrons from the 6 carbon monoxide molecules, and finally it can acquire the xenon atomic number. So that is the stable electronic configuration. So and then another example is osmium pentacarbonyl. So what is the electronic atomic number of the osmium? Means 76. So it is having the 10 electron deficiency. So to the radon atomic number. So therefore it can acquire the radon atomic number 86. So by gaining the 10 electrons from the 5 carbon monoxide molecules. As a result it is having the formula OSCO5 CO5 times. That means it can acquire only the 10 electrons. So that's why it can combine with the 5 carbon monoxide molecules only. So these are the general EAN rule that can be applicable. So while the another example in this particular last row, that is MnCO 5 times. So here the atomic number of Mn is 25, and then it can gain electrons from the 5 carbon monoxide molecules, 10 electrons. So therefore it is having the electronic configuration, that is 35. 25 plus 10, that is equal to 35. It is not the electronic configuration of inert gas. It is an exemption. So here all of the above examples, in all of the above examples, the atomic number of the metals or the even numbers 26, 24, 28, 26, 42, 76. That means EAN rule can be applicable for the metals, so which are having the atomic number follows this EAN rule. So that's why, so those are the metals like MnCO, and then like odd atomic numbered elements, so cannot follow this particular EAN rule. This is an exemption from exemption of or the limitation of EAN rule. And first one, vanadium hexacarbonyl. So vanadium hexacarbonyl has an octahedral geometry. It can forms 6 coordinate covalent bonds. So by with the 6 carbon monoxide molecules. It is isostructural with the chromium hexacarbonyl. So similarly, and next slide we can discussing about the chromium hexacarbonyl. So both are isostructural. So both are having the same octahedral geometry. So or isostructural to each other. There's a point. So because even though they have the different valence electron count, and they doesn't having the same number of electrons, even though they do not have the same number of electrons, they are isostructural with each other. The high resolution X-ray crystallography indicates the molecule is slightly distorted. So that means all the vanadium carbon monoxide bonds are not equal. Some of the bonds are that is 2 axial bonds, up and downward bonds, 2 axial bonds are shorter. That is distance is 1.993 angstrom units, whereas the 4 equatorial so bonds, and vanadium chromium bonds are somewhat longer, that is 2.005 angstrom units, and it follows the 18 electron rule. So that is the vanadium hexacarbonyl, and then the chromium hexacarbonyl. So in this particular chromium, it is having the all of the metal carbonyls, so majorly have the zero oxidation state, and it is a homoleptic complex. What is it? Homoleptic means that particular complex that is having the same type of ligands. Such type of complexes are called homoleptic complexes. The complex is octahedral, and then here the chromium carbon bond is 1.91 angstrom units, and CO distance is 1.14 angstrom units respectively. All of the bonds are in this particular chromium hexacarbonyl are seen in this structure. And then manganese decacarbonyl. This is the polynuclear metal carbonyl, very important metal carbonyl. MnCO5 unit, those two units can be linked through manganese bond, MnMn bond. Here there are no bridged ligands. What are that bridging ligands? Means same ligand can be linked to two metals. So ఒకే ligand రెండు metals కి లింక్ అవుతుంది. So in this molecule there is no metal there is no bridge such type of bridge ligand. So that it can be described as the two units linking of the two units, that is MnCO5 and MnCO5. There are two kinds of carbon ligands, that is four ligands, or in the diagram different four ligands, two ligands or the dashed wedges, and two ligands or solid wedges, and these are the four ligands or one type, and one of the carbon monoxide of manganese and another carbon monoxide of the another manganese or coaxial with MnMn bond. That is the two carbon monoxide molecules and two manganese atoms are in the same line or in the same axis. So the MnMn bond is bond distance is 2.93 angstroms or 293 picometers. The remaining four manganese, the remaining four carbon monoxide molecules are perpendicular to this particular MnMn axis. In this particular manganese decacarbonyl, so that is two units are there. So the MnCO5 unit and another one is MnCO5 unit. So these two units can be rotated so through MnMn bond. So that is a stable rotational isomer, that is a formation. All those particular so Mn and CO bonds are somewhat far distance and somewhat big distance or large distance from each other, so that they have the least repulsive interactions, while in the eclipsed conformation the metals and the carbon monoxide having some experience from the intermolecular repulsive forces, so that it is unstable. So that's why the Mn2CO2 10 times has an so staggered conformation. So these are the basic structures of some metal carbonyls. Overall, in this video we discussed about the definition of some metal carbonyls, classification of some metal carbonyls, the differences between the metal carbonyls, that is the mononuclear metal carbonyls and the polynuclear metal carbonyls, and then EAN rule, EAN approach of the metal carbonyls. So some examples of the EAN rule so we discussed in this particular video, and then the structures of some metal carbonyls, that is vanadium, chromium and manganese carbonyls. This is the metal carbonyls part 1. Thank you.